So last time we introduced the geometric distribution, we talked about what it actually is. And do you all remember? Can you kind of describe it?
Probability of some events happening in a recurrence interval.
Yeah. There's a couple of ways, and that's so. What Sam just said is the probability of an event happening in a recurrence interval. And you could think of that, and because the geometric distribution, it's discrete. And so we're thinking about trials, Bernoulli trials. We could think of it two ways. We could say, what's the probability that our random variable n takes on some value before our first success? Or we could just say event occurring. This would be our PMF. And then we could also say, what's the probability that n is less than or equal to some value? So number or probability that, let's see, this would be the event occurs for the first time. We'll say within n trials. So that was how we introduced it, but then we went on to talk about recurrence interval or return period. Those are interchangeable terms. Recurrence interval, I think, is a little more statistically sound, but return period, you'll hear a lot out there. The 100-year return period, 100-year flood, something like that. We can also kind of flip this on this neck and say, what's the probability? What is the, we'll just write that up here, recurrence interval. And this is the average number of trials between successive events. Oh gosh, successive. Oh, did I get that? Successive. I really struggle with double letters. So many C's, so many S's between successive events. And so when we first defined it, this is what's the probability that it's going to say it takes 10 flips before we get to our first heads, right? Or what's the probability that we get a hedge within 10 flips? This would be I didn't write that up, this is the CDF. And then we can say, okay, well, what happens with the next one, right? What's the probability that, what's the average number of flips it takes between heads? Or we could think of it more engineering applications of what's the recurrence interval between events, a storm event, a spike in contamination in the incoming sewage stream, right, for a treatment plant or something like that. So then you can start thinking about the time period in between. And we define the expected value. So if the recurrence interval is t, the expected value of t is equal to 1 over p, where p is the probability of events within a trial. So this could be a trial, could be a year. It could be a coin flip. It could be a day. It could be some discrete thing that we slice it up as. And so there's this nice relationship between t and 1 over p. Or t average, like this is the average recurrence interval. All right, geometric distribution. Now we went into the recurrence interval, and now we're going to go a little bit deeper, and we're going to talk about what's called the risk equation. And we're going to use this. Risk has a lot of different terms. I'm going to call this probabilistic risk. So I work in kind of hazards to some extent in my research and consulting, and risk is used a lot in a lot of different ways. So you have to be kind of specific about what you mean by risk. There's a kind of a classic definition of risk where this is, we'll call it economic risk. And this is equal to the probability of some event occurring times the consequence. And that could be money, it could be lives, it could be damaged infrastructure, that sort of thing. Some valuation of that. And so we could say, what's the risk of this bridge failing in this given year? You could also extrapolate it out to many years, right? And so we have kind of in a given year, the probability, say that's 1% times the bridge failing, that cost $1 million to replace or repair. Then we get the kind of economic risk in a given year. While we're on that topic. So let's think about, so we'll just say observe that the probability of no event occurring within a return period is, what's the probability of no occurrence? So probability of no occurrence within T, where each year, we'll just say each year is a trial. So what's the probability of no occurrence in 1 year? Where P equals probability of occurrence in a given year. So if P is our probability of occurrence in a given year, what's the probability of no occurrence in a given year? 1 minus P. So this is in a given year, and then if we're going to say that, these are Bernoulli trials, each trial is independent, so we're going to say each year is independent. We can go into whether or not that's true, but we're just going to raise it to the T. So we don't occur in year 1, we don't occur in year 2, we don't occur in year 3, so we're just going to multiply them together. Okay, so we can use the binomial theorem, and assuming large T and small p, and you're going to play around with this. What does large T and small p mean? P of no occurrence within T, which equals 1 minus P to the T, it can be approximated, in the limit essentially as T gets big and as P goes small, e to the negative TP. And we know that, T is equal to 1 over P. So we get e to the negative 1, which gives us 0.368. So there's basically a limit here. As our recurrence interval gets bigger and as our probability gets smaller, we get essentially a constant value. The probability of no occurrence within a recurrence interval is about 0.37. So we can take the complement of that and we can say the probability of occurrence within T is equal to 1 minus e to the negative 1, which is equal to 0.6. 3, about 63%. And that applies again to bigger T's and smaller P's. So for one of the assignments, the like little assignments I have on campus, you'll explore that for this. So what this means is that relatively rare events which means, large T and small p, because, they're related, right? T is a function of P and vice versa. For example, the 100-year flood or the 1% annual chance flood. We should just say, let me just rephrase that just so our sentence makes sense. Relatively rare events have a probability of occurring within their recurrence interval of about 63%, not 100%. And that might be a little counterintuitive if you think about, we'll just go back to the 100-year flood example. The probability of you'll experience a 100-year flood within a 100-year time frame is not 100%. And that's just the way the math works, right? Because we're doing this kind of multiplying probabilities together and raising them to powers. So in fact, it's only 63%. Let's do a quick example, and then we'll get into the risk equation. This is all leading up, very, very suspenseful. Now, so for this example, we're going to calculate the probability of a 100-year recurrence interval, RI, also known as the 1% annual exceedance probability. So 100-year, 1% annual flood. Occurring, actually, we'll just say impacting. Impacting a home built in the 100-year floodplain. Over its 30-year mortgage. So this is kind of like a classic floodplain management problem. You've got a home, a development, it's in the floodplain. We've mapped the floodplain. We know where the boundary is for this particular recurrence interval flood. And the FEMA floodplain insurance program, National Floodplain Insurance Program, is set up to be like, okay, you got a mortgage, you got federal backing of that mortgage through Freddie Mac or Fannie Mae or whatever it is now. You've got to have flood insurance. So that's the kind of national floodplain policy that we have. You have to buy flood insurance if you have a mortgage, essentially. If you don't have a mortgage, it's up to you. So what's the probability? So mortgages are typically 30 years. It's like the standard mortgage. What's the probability that you're actually going to get flooded in that 30-year time frame? So we know that our probability in a given year is 1%, 1 over P. And we can look at a couple things. We can say the probability of no floods over 30 years. We can do that one. We just did that up front, but that's 1 minus p to 30. So 0.99 to the 30. And that gives us a probability of 74%. Not too bad. It's only 30 years. Pretty good odds. But what's the probability of actually getting flooded? We'll just say at least one. And that's really just 1 minus 1 minus 1 minus p to the 30. And so that gives us, of course, 26%. So not great odds, right? 1 in a quarter, right? 25%, 26% chance of getting flooded. So this formulation is what we're interested in right here. What's the probability that something's going to happen over a certain time frame? And this essentially is what I'll call as the probabilistic risk equation. If I can write it up. Okay, so say we want to design something. That can withstand some events. With a certain annual exceedance probability. Also known as AEP, and annual exceedance probability is the probability that it is equaled or exceeded. All right, and we'll call that P. So that's just our annual exceedance probability. The 100-year flood has an annual exceedance probability of 0.01. So we'll use this formulation. It's basically the same problem. The probability of at least one flood that's equal to or greater than a certain magnitude over so many years. So we can look at this risk. What's the risk that this is going to happen? And so we'll say big R risk is equal to 1 minus P to the N. And this is the risk or probabilistic risk of an event with AEP of P. I think it's just 1 R occurring over N years. It's a very simple equation. It's a very powerful equation. I'll use my example of stream restoration again. I designed a river restoration project. It incorporates a lot of vegetation. That vegetation needs about 5 years really for the root structure to get in there and to kind of stabilize the banks and that sort of thing. So I want to know what's the risk that I'm going to get a flood event, we'll say, of a certain magnitude, maybe if it's above the, we'll say, 2-year recurrence interval event, within the first 5 years, what's the probability that's going to happen? And that could essentially maybe not destroy, but I'm going to have to go back and do some maintenance. And so I can calculate that probability, maybe even factor it into the budget so that, if you want a flood to happen on a river, go and do a stream restoration project. It's the same as washing your car and having it rain that day or the next day. It's literally uncanny. Of course, we're in a drought right now, so maybe we're okay. But say, so we'll do that stream restoration example. I'm interested that in the 2-year recurrence interval, so that's P is 0.5, that's the 2-year flood. And I'm interested in, I need about 5 years for things to firm up. So what's the risk of that 2-year flood occurring in the first 5 years? It's probably pretty high, right? 1 minus 0.5 to the n, to the 5. Can someone calculate that for me?
Six.
96.8%. Okay, almost guaranteed to happen. So maybe I do want to budget in that maintenance, right? And we know it's going to happen. You could do this a little bit bigger. You're like, okay, I'm going to design a bridge so that it can withstand the 100-year flood. So my P that I'm designing for is the 100-year flood. And the bridge actually has a design life of 50 years. So I'm interested in a 50-year design life. So what's the risk of that 100-year flood occurring over 50 years? Let's run that one. Okay, so we'll say 39.5, so we'll say about 40%. 40% chance. And so now I know, okay, well, this is what I'm looking at. And I can kind of think about long-term budget. What happens if it's equal or exceeded? What kind of repairs can I expect to have? And I can actually do this economic risk calculation, right? Where I say my probability of occurrence over that lifespan is 40% times whatever the cost is going to be to fix it. And then I can do some more, like net present value type of calculations to actually bring that in, right? So this would be probabilistic risk. And then this would be economic risk. So this is interesting. Okay, what's our risk? But then we can invert this equation. To solve for P given a certain risk tolerance. Now, why don't you guys take a couple minutes to do that, and then we'll write it up together. Okay, so if we start with our risk equation, R is equal to 1 minus P to the N. We solve for P. We end up with P is equal to 1 minus R to the 1 over N. So a little bit funky there, but we can use this then to figure out what kind of event do we need to design to if our risk tolerance is fairly low. So we, it's a major project, it's an interstate system, and if it fails, it's going to cause millions of dollars of economic damage, just like what happened in Glenwood Canyon, right? So what if we're going to go into Glenwood Canyon and redesign some of those bridges, or bridges that don't exist because it was just a tiny little culvert and then a debris flow, went over it. In hydrology, we will have a presentation on this. They designed these little culverts to be like 6 by 6 feet. And then we had a freaking debris flow of like millions of cubic or hundreds of thousands of cubic yards of material come through there. So, maybe they needed a bridge, but bridges are expensive. So if we design that bridge, what's our risk tolerance for an event that could overtop it or shut the highway system down? So we can say, okay, so say our risk tolerance over a certain design life a risk tolerance for failure of some kind, right? Maybe it's not catastrophic failure, maybe it's like thing shuts down or something like that. Over to certain design life of n years is, we'll say, 10%. For 10%. And you can do the economic analysis to figure out what that risk tolerance is. Okay, so 10%. And say for a design life of 50 years. Typical design life for bridges and that kind of thing. So let's calculate what P or annual exceedance probability should I design for. So we can use that inverted equation to do it. So let's do that. So P is equal to 1 minus 0.1 to the 1 over 50. And that ends up being 0.002. Tiny probability. And that's the annual exceedance probability. So what's the recurrence interval associated with that? So we're going to design for the 500-year storm, or flood, or debris flow, or whatever that is, wind event, hurricane event. Now, just a little bit of discussion on this kind of thing. This comes up a lot with just infrastructure in general, especially in this world we live in where, storms are bigger, more intense, more frequent. In Texas and Houston, they had essentially back-to-back 100-year floods or greater than 100-year flood events. And so we were like, what's going on? Like this, the probability of back-to-back events isn't zero. We know that you can have 200-year flood events because each year it's just up 1% probability, but it's low, 1% times 1%, but it's not impossible. But what are we doing here? Like, are we doing the right thing? And this idea of designing infrastructure to the quote unquote 100-year event, it's a standard thing we've been using for decades. Bridges, highway systems, like a 100-year event is this standard for some reason. We just decided that's a big number. Anything bigger feels like a little too much, maybe too expensive. So we're gonna run with it. But come to find out, maybe we're not doing such a good job. There's a couple of reasons for that. One is, I think, the science indicates that our climate's becoming more variable. We have more water in the atmosphere with a warmer atmosphere. And with a warmer atmosphere, we have more energy in general. And so things are just more intense. There's just more energy for thunderstorms. There's more energy, there's more water in the atmosphere. So we could have more frequent flooding events, hurricanes, tornadoes, that sort of thing. And it's playing out. And so the discussion then becomes, well, what is a design standard that works? The information of what a 100-year event is based on a stream gauge. And that stream gauge for a flood may have a record of 80 years or 50 years or 30 years or something like that historically. But the history may not be a good reflection of what's to come. So if we build something now, it's going to last for 50 years into the future. And so if we look at 50 years in the past to determine what to set that bridge deck, how high to set that bridge deck based on the stream gauge record and a statistical analysis of flow, then we needed to look forward either with models of climate projections or come up with a better standard based on our historic data. If we think that we're becoming more variable than what was happening in the past, then let's give ourselves kind of a higher threshold for our design, in which case that 500-year event, much less frequent, bigger magnitude events might be a better design standard for certain things, like critical infrastructure. Let's build hospitals and daycare centers and fire stations outside of the 500-year floodplain instead of outside of the 100-year floodplain. Because now we're seeing that the 100-year floodplain is no longer like working for our infrastructure, our society. It's causing economic damage, etc. So this is, right now, it's really just a conversation. People are advocating for this, like the engineers, the floodplain managers, but it hasn't really become policy. So that's what we're looking at right now. Yeah. So it's happening in a lot of different levels. FEMA is the agency that, I'm gonna pause this, stop this real quick.